In this video, we're going to look at using substitution to evaluate definite integrals this time. So in the previous couple of videos, what we were looking at is using substitution and various substitutions we can make to tackle indefinite integral problems. But here we're going to use that same strategy, but use it in the realm of definite integrals. Really nothing changes. All that we really have is bounds on our integral now that we're going to use the evaluation theorem with to figure out an exact value that this integral takes. Okay? So let's go ahead and look at what we're doing. We're going to use the substitution u equals x minus 6 to evaluate this definite integral. Okay? So part 1 tells us to rewrite our definite integral in terms of u, and it tells us this key piece here. Remember to use limits of integration for the function u as a function of x. Let's explain what that means. The bounds that we have on this definite integral are in terms of x. Okay, let's kind of keep that in mind. Well, what happens when we make substitutions with u and du and change this entire integrand into terms of u? These bounds of integration that were originally for terms of x are no longer carrying the same specifications that they were with x, right? Like we no longer have the integral on from -2 to 1. We have something else where we've translated our integral into terms of u, right? So just like we've translated our integrand into be terms of u, we also need to translate our bounds of integration to be in terms of u. Okay? So what does that mean for us? Well, since these bounds of integration were in terms of x for us, what we can do is we can plug these x values, or our bounds of integration, into our u, our function of x, to figure out what u of a and u of b are going to be, and we can change those bounds of integration so that our whole problem has now changed from a integral in terms of x into an integral in terms of u. Okay? So what that means for us is we're going to do the same thing we did with the indefinite integrals of changing everything that we see with an x into terms of u, and we're also going to do the same thing for the limits of integration. Okay? So before we keep talking about it, let's actually do it and explain it as we do it. So here we have u as a function of x. Then if we apply the definition of the differential, we get that du equals the derivative of this, which is just 1. So du is going to be f prime of x, or 1, dx. Okay? So here we have this function of x is our u, and then we have dx is going to be defined as just du, right? So if we make those substitutions, what we're going to get as our integrand is 3 over u squared du, right? Well, then we talked about how changing the integrand in terms of u, when we're dealing with a definite integral, we also want to change our bounds of integration from being in terms of u, or from being in terms of x, to being in terms of u. Because if we do that, we can just integrate this whole problem straight away and not have to worry about substituting our x's back into this problem to worry about doing that, and then integrating with respect, or then evaluating with respect to these bounds. By changing our bounds to be in terms of u, we're tackling this whole problem in terms of u so that it essentially nullifies any bit of substitution back in with x into our antiderivative and then having used the evaluation theorem on it. Does that make sense? Because if we evaluate this integral from -2 to 1, we're not going to get the same original expected value that we would evaluate this antiderivative to be. Instead, what we would get is something like really kind of bizarre unless we substitute back in our x terms in for our u. And what that does is just adds in a lot more work to the process. This whole changing everything to be in terms of u is going to help us because it kind of cuts off a little bit of that busy work inside of this process and lets us just kind of keep going with all this in terms of u, and it's going to give us the same answer that we would have in terms of x by doing all those substitutions. So let's turn our bounds of integration into terms of u and then move forward with this problem. So to translate our bounds of integration, what we're going to do is we're going to plug in -2 and 1 into our u function, or our function in terms of x right here, to evaluate what they would be in terms of u. So essentially what that means is we're going to take u of -2 and u of 1 inside of our function here and see what they become. So this becomes -2 minus 6, or -8. and this becomes 1 minus 6, or negative 5. Okay? So our bounds of integration in terms of u are now going to be negative 8 to negative 5. And what we've done is we've changed this entire integration problem that we had in terms of x into a problem in terms of u in every capacity. The reason why we couldn't do this with indefinite integrals and we had to do the substitution back is because with definite integrals, we're going to get an evaluation here, right? But since we changed everything to be in terms of u, we're going to get the same answer that we would get if we were making this switch back and integrating with respect to these bounds after we integrated with respect to u. Okay? So whenever we do indefinite integrals, we've got to make that switch back because our original argument was in terms of x, and we're not doing any further evaluation to give us like a numerical answer. We're trying to find the general antiderivative in terms of x, right? But here, when we're doing a definite integral, we're going to find our antiderivative, but then we're going to evaluate it at specific values. And since we evaluated the antiderivative with respect to u, in this case right here, if we change our bounds to be with respect to u on top and bottom of this integral, we can use that in our evaluation theorem instead of having to plug x's back in for our u's and keeping the same bounds of integration that we have here and just doing a lot more work than is needed. So kind of moving forward from all that spiel now, we're going to go ahead and, since we've rewritten the definite integral in terms of u in every capacity, we're going to satisfy part 2 right here and evaluate this whole thing. Okay? So the first thing we need to do is take our integral with respect to u. So what I'm going to do in order to evaluate this first is I'm going to translate this term to where I'm not dealing with a fraction, but I'm going to use a property of exponents that we know, or maybe we have learned in the past and maybe have forgotten. Maybe just kind of going to bring it back up. What I'm going to do is I'm going to take this term in the bottom, this u squared, and bring it to my numerator by negating the exponent. Right? Because there's a property of exponents that tells us if we have a negative exponent, in order to make it positive, we just take it to the other half of the fraction, right? Well, I can also make a positive exponent negative by taking it to their half of the fraction, right? The reason why I did that is because now I have this term here that I can integrate by using the power rule, right? So if I take the antiderivative of the thing that's inside of here by using the power rule, I'm going to add 1 to this power and then divide this entire term by that power, negative 2 plus 1, right? So here what I'm going to get is 3u negative 2 plus 1 is negative 1, and this is all going to be over negative 1 again, right? And so then this is going to be evaluated from negative 5, or negative 8 to negative 5, rather. So we see how that works? I went ahead and took this u squared that's in the bottom of this fraction here and moved it to the top so that I could evaluate this using the power rule instead of trying to use another form of integration that we may not have access to yet. Okay, so I went ahead and just kind of went back to the power rule by using a simple law of exponents. I used the power rule, did the antiderivative, and it gave us this. Okay, well, what does this translate to? Well, here we can make this negative exponent positive again because we're done integrating it now, right? So we can translate it back to what we had before. So what this is going to give us is negative 3, because 3 divided by 1 gives us negative 3, over u, right? And we're still evaluating this from negative 8 to negative 5, right? So all we really did was we used the law of exponents to do something, and then to undo it later, just because it makes the integration on us simpler to do it, and then it makes the evaluation simpler to undo it. And the reason why I say that is using the evaluation theorem, what we're going to get now is negative 3 over negative 5 minus negative 3 over negative 8, right? This is what we're dealing with now in terms of our evaluation. So what we're really looking at by using algebraic properties here, negatives divided by a negative is going to be a positive. Then we have minus a negative divided by a negative, which is going to be a positive 3/8. So now all that we really have to do to finish evaluating this integral in terms of u that we started with, right? All we really have to do to finish it is to do this fraction subtraction here. What do we need in order to subtract fractions? We need a common denominator, right? And we see that our common denominator between these two fractions, or these two denominators rather, is going to be 40. So we need a common denominator of 40 in order to subtract these fractions. Well, in order to go from 5 to 40, we multiplied by 8, so 8 times 3 is 24. And then if we multiply or to get from 8 to 40, we multiplied by 5. So we've also got to multiply 3 by 5 to give us this. Because the factor that we change our denominator by is going to need to be also the factor that we need to change our numerators by in order to give ourselves equivalent fractions, right? Well, now we have 24 over 40 minus 15 over 40. So all we do is we subtract the numerators. So 24 minus 15 gives us 9, and that's over 40. So this is the evaluation of our original integral. And this would be what we evaluate our integral to if we use everything in terms of u, like we did here for this problem. We changed our bounds of integration to u and did all this stuff in terms of u without ever substituting back in x minus 6 equals u and using the original bounds of integration. But this would also be what our original integral up here evaluates to. And the reason for that is that u substitution is an integration technique, right? We kind of let u equal this function in terms of x to simplify down our integration so that we can do it. And then in terms of doing the integration, we actually had to use some exponent properties to get us to this point, right? But if we so desired, instead of changing the bounds of integration to be in terms of u like this for our function that we plugged in as u, integrating everything with respect to u, what we could have done is stuck with those original bounds of integration, -2 and 1 here, and then instead of taking this next step of doing all this, just substituting back in x minus 6 equals u, and then evaluating all of this stuff in terms of x. Does that kind of make sense? We would just kind of do what we did for indefinite integrals and make this substitution back at this point so that we had an antiderivative in terms of x. And then to use the evaluation theorem, what we would have done at that point is to also have evaluated our antiderivative at those x bounds of integration. Okay, so either strategy is perfectly valid, but typically what we like to do for kind of simplicity's sake is using this whole change everything to be in terms of u. Change the integrand to be in terms of u, and if we're dealing with a definite integral, change the bounds of integration to also be in terms of u. It just takes one less headache out of the equation for us in terms of making more substitutions and then evaluating all these things just to kind of get to the same answer, right? This flow of work worked a lot in a lot less steps than it would have if we tried to make this switch back to x and then evaluated with these bounds, right? If you don't believe me, you can go ahead and stop at this point here, substitute u equals x minus 6 back into this equation, so we'd have -3 over x minus 6, and then do the evaluation theorem from -2 and 1, and see kind of how many more, it wouldn't be that many more steps in this case, but for the most part, it's going to add in an extra step, because essentially what we're going to have to do is evaluate 1 minus 6 and -2 minus 6, like we did right here. And by leaving all this stuff in terms of u, we've essentially like leapfrogged that, and we've kind of avoided it, and we didn't have to take that unnecessary detour and do all that. So that's really why we like to do this and put everything in terms of u, is because it heads off this problem at the pass of having to do all this stuff by substituting back in, like substituting all of our x terms back into the problem, and it just makes it like just one less step to deal with. Like I've said, and I've probably repeated that like 7 times by now, but in summary, whenever we're doing definite integrals, whenever we change our integrand with respect to u, we also like to change our bounds of integration to be in terms of u, so that we don't have to worry about substituting and switching back and then doing the evaluations with respect to x.